just talk about this idea that work depends on path. In this video, I want to sort of take that a little bit further to actually thinking about trajectories that particles can follow and using those in order to figure out what the work is that is done along those paths. And in that context, what we're going to do is actually finally get to this sort of idea of energy flow as being that word power is energy flow, that is the rate of change of energy in time. So you remember that when we talk about work, right, the work that's done by an interaction is the integral along some path from the starting point to the ending point of the force that interaction is exerting on the object, which is, of course, a function of the position that you're in, dotted with a little change in the path. So I want to think about a sort of generalized case now where I've got some object that's moving from point A to point B, and it's moving there along some path, right? So here's my path. Okay, so it could be that I'm interested in how much work drag is doing on an object, or how much work the object is doing on drag, you would actually say, or how much work the gravitational field is doing on an object. So there are a variety of interactions that could be doing this work. But the key idea is that we've got some force that's defined, and we've also got some path that's defined. Mathematically, I want to define that path as a position vector, right? And a position vector as a function of time. So I've actually got a position that the particle's at as time goes on, right? So this is like r at t naught, and later on, like this is r at the time t2, right? So the idea is this vector is sort of sweeping out that path. And obviously, if for any given force, you could imagine that the force that you're interested in, right, might be some function of where you're located, right? So for example, gravity is an example of a force that depends on location, right? It could also be a function of how fast you're going, right? So for example, drag depends on how fast you're going. And it could be a function of other stuff too, for example, different characteristics of the object here. So for example, drag also depends on what the cross-sectional area of the object is and what the drag coefficient of the object is. But in general, the force potentially depends on position and might depend on other state variables as well. Okay? So how do we actually figure out what the work is then? Well, we want to integrate from point A to point B. This force, which is a function of position, which is a function of time, right? And also a function of velocity, which is a function of time. And also potentially a function of other things that maybe don't depend on time, like what the mass of the object is. And that's then dotted with, I'm going to call it dr, right? Where dr is a little chunk of the path, right? So it's the change in r over some little bit of time. So this is like r at time t plus delta t. This is the point r at time t, right? So dr is this position vector minus that position vector. In other words, it's this little vector here. Right? Now, if you think about it, that dr is actually something that we already know how to figure out, right? Because that's tangential to the path. It's the distance that the object travels along that path in some time delta t. So we actually could think about dr as simply being the velocity of the object as a function of time times a little chunk of however much time passes, right? So at each point along this path, like maybe here the object's moving really fast, so dr for a little chunk of time here is relatively long. Maybe here it's moving a little bit slower, so dr is smaller, and it's always, of course, oriented in the direction of the velocity. So now I can actually think about this work as a much more sort of explicit integral, and it's a single integral with respect to time. So from time is equal to t naught to the final time. I'm going to integrate whatever this force is that I'm applying, which depends on position, which depends on time, which depends on velocity, which depends on time, dotted with whatever the velocity is, that depends on time, dt, right? So here inside we have a bunch of stuff, but that stuff at the end of the day is simply some function of time. If we look at what that stuff is, it's actually just a force dotted with the velocity, right? So whatever the force is that you're applying or that interaction is applying dotted with the velocity tells you how much the work increases over a little bit of time dt. In other words, this quantity is the time rate of change of the work, right? Or the power that the force is supplying. All right? You'll notice it has units of force times distance over time, right? Or energy per unit time. That joules per second is also referred to as watts, right? That's the units of power. And so if you know how fast an object is moving and in what direction, and you know what the force is at that location, you can actually ask the question, how much energy is that force either pouring into or pulling out of the thing that you're applying the force to? Okay. So we can now sort of come back and think about, say, the spring example and ask the question, well, what's the power in that spring example, right? So if I think about power in this case, right, let's say we start out with the mass stretched, right? So this is point 1. This is maybe the relaxed point. This is point 3, right? Pretty clearly at the stretch point, the velocity is 0, so there's 0 power at that point, right? At this point, right, the force that the spring is applying is 0, so there's 0 power there. And at point 3, the spring is completely compressed, the velocity is 0, again there's 0 power. But in this region, right, the force that's being applied is to the left, right? And the velocity is to the left. So in this region, power is greater than 0, right? There is power actually being poured from the spring, or there's energy being poured from the spring into the mass. In other words, the power that is being supplied to the mass is positive, so you have some number of watts going into the mass. In this part of the motion, the spring is actually pushing backwards, right? The velocity is still to the left, so the power, F dot V, is negative in that component in this part of the time while the mass is slowing down. And so that means that you've actually got the spring sucking energy out of the mass. You've got energy being transferred from kinetic energy to potential energy. And so this sort of power idea relates to the sort of stock and flow picture here. Right? We've got kinetic energy and potential energy. And the various forces that are being applied to the object. If the forces that are being applied to the object are positive, you're getting power into the kinetic energy. If the forces that are being applied to the object are negative or positive into the interaction, you get power being poured into the potential energy.